In this video, we are going to talk about an application of graph traversals. We define graph interface. The graph interface has a whole bunch of transformers and observers, such as adding a node to it, establish an edge, find out if a vertex is inside any of the nodes inside the graph, so on and so forth. Graph traversal is a mechanism that you can apply on top of the graph. So graph traversal is an algorithm commonly refers to as visitation of every single vertex inside a graph in some order. So a depth first search is a traversal that visits a starting vertex. It visits every vertex along each path, starting from that vertex to the path's end before backtracking. And so that's depth first search. There's also a breadth first search. Both traversals look exactly the same from a mechanism standpoint. For depth first search, we use stack, and for breadth first search, we use queue. These are the two applications of graph traversal that we will take a look at. There is a use graph Java class. This one is solving the shortest path problem using the airport example. So you can also come up with your own graph too. But fundamentally, to find a shortest path means we have to ascertain all of the paths out there, right, in a graph. Ascertaining all of the graphs out there requires some traversal mechanisms. In this application, you see is path BF, that's first search. There's also a is path BF, this is breadth first search. There are two mechanisms of traversal that you use to solve the shortest path problem involving a graph. Have a look at this. There's a main giving you all of the examples. Let's go through the specific graph traversal, the depth first search strategy, and there's also a breadth first strategy. We'll examine depth first search and then the breadth first search one at a time. So this is the Austin to West to Washington problem. So let's just use Austin to Washington as an example. The problem that we're trying to solve is, suppose you are in Austin airport, your flight destination is Washington. Can you get from Austin to Washington through any routes? As you can see, we're not looking at the shortest path. We're looking at a path exists between Austin and Washington, bypassing any number of intermediary cities. The answer is yes or no. Let's solve this problem. Let's use depth first search. This is just a pseudocode. And depth first search involves use of a stack. The concept of backtracking, right, is always there. So just remember depth first search, stack, backtracking. Breadth first search, which is the level order. Level order involves queue. In the beginning, let's just initialize the whole system. You will clear all the marks. Marks means visitation labels. Have you visited this node? So in the beginning, let's just clear all that. We want our solutions to be reusable. You want to set found to false. Is path. This one returns a Boolean. Is this path exists between this vertex and this vertex? The start vertex in our example is Austin. Our end vertex is Washington. This returns a Boolean. Mark all of the start vertices, basically saying that, hey, I have not visited all other nodes, but I visited my start vertices. So mark it yes. That's the starting point. And then you push the start vertex into a stack. This is the do while loop. The initial condition is established. You push the start vertex. So in your tree example, the start vertex is at root. These two operations basically gets hold of the top of the stack, which is your root or your start vertex, and then you pop it. In some programming language, this is a one-step operation. You can pop it. The pop itself returns a vertex. There are two criteria that we will be checking. One is if the current vertex is equal to n vertex, then we found it. Then you set it to true. If this is found is true, this is going to immediately break out of the node and return found, which is true. Most of the time, you're not going to find it. So this else takes place for each adjacency matrix. So this one may have two routes. For each adjacent vertex, basically taking it, this one as a one and this one as a second. The first one is going to be pushing to second. If this adjacent vertex hasn't been marked, meaning visited, then mark the adjacent vertex as yes, I'm visiting this node, I'm marking it as visited, pushing to the stack. This is going to allow you to push the very first one into the stack if it hasn't been marked. If marked, then you don't visit, but if not, then mark it. So these two have been marked and pushed into the stack. So initially, you're going to have this guy here in the stack as well. This for each, it's going to do an internal loop. One is done and visit the second one. The second one is going to be pushing to the stack if not marked. There is no difference whether this is one or two. When you initially construct your graph, Your down node here might be the first one in. In that case, then the adjacency vertex is going to pop out first. As you can imagine, this loop just keep going. So this is a visualization on the left side. Let's just start off with AU, Australia, or Austin. There are two adjacent nodes, this one and this one. AU has Houston and Dallas. When you iterate adjacent vertices for AU, you're going to have DA and HO. DA is the first one and Houston is the second one. This is the initial conditions here. You set found to false, clear all the marks, and then mark the start vertex. So we marked AU right here. And then we'll push AU onto stack. So this is your preconditions here before you do while right here. As long as stack is not empty and it's not found, just keep on going. This entire loop, just keep going. Now you're entering the do while loop. We remove AU from the stack because we're popping it. We're setting it to a vertex stack top, pick the AU out of the list and then pop it. So these two lines are implementation details. We process AU as in checking to see if AU is actually the one that we need. If not, just keep on going. This is a loop number one. This is a loop number two. Mark DA. Why? AU DA. The first adjacent list is DA. And AU was marked all the way on top. And then we mark DA. Meaning I just visit it, then you push DA into stack. So this is the very first iteration inside here. AU has another mark, another adjacent node, HO. Mark HO and push into stack as well. DA and HO. But AU is gone because you just popped it. Upon the very first iteration, we're at step B, you got DA and HO. And this is stack, which means last in, first out. Last one in, first out, and out. So the very first one that gets popped in your next iteration of while loop in step C is HO. DA is still there because DA is on the bottom of the stack. So HO is popped and HO's adjacent node is AT. This AT is going to be marked and then pushed into the stack as well. So at the end of it, you have DA and HO. In the fourth iteration, AT is marked, HO is marked, AU is marked, so is DA marked. Remove AT from stack. So this is the first two line implementation details that we're talking about, these two lines. Process AT means checking to see what's going on with AT. Is AT the one that we're looking for or not? If not, then skip HO. HO was visited. You don't want to visit again, so we skip it. And then we mark Washington, WA. Now you have DA and WA. Now we're going to have to remove WA. Now we're in our fifth loop. In the fifth loop, remove WA. Remember, this is a mark. This is a mark. HO is marked. AU is marked and DA is marked, meaning we've visited those already. This one is going to be true, these two lines. Since found is true, your while loop says not found. So this one is going to exit out of the loop and return found. This means there is a path between AU and WA. The entire mechanism makes use of depth first search. This is depth first search because we're using stack to traverse the entire tree to see if a path is possible between the two vertices.